The date is August 18, 1940. The sun hangs low over the English Channel, casting long shadows across the cliffs of Dover. In a cramped operations room carved into the hillside, 37 pairs of eyes stare at a plotting table that has suddenly gone dark. The room that moments ago buzzed with urgent voices has fallen into a terrible silence. Someone drops a pencil. The sound echoes like thunder. Outside, high above the channel, more than 400 German aircraft are approaching the British coastline. Messerschmitt fighters escort Heinkel and Dornier bombers in formation so vast it would take a man 3 minutes just to count them all. They are invisible to the naked eye, still 30 miles offshore, but they are coming. And right now, Britain is blind. The radar has failed. To understand what happens next, you need to understand something fundamental about the summer of 1940. Britain stood alone. France had fallen in just 6 weeks. The British Expeditionary Force had barely escaped from Dunkirk, leaving behind nearly all their heavy equipment. Hitler's Wehrmacht controlled Europe from Norway to the Spanish border. The United States remained neutral. The Soviet Union had a non-aggression pact with Germany. Britain faced the largest military machine ever assembled, and the only thing standing between the island nation and invasion was the Royal Air Force. But here's what most people don't understand. The RAF wasn't winning because they had more planes. They didn't. German intelligence estimated Britain had about 1,500 fighters. The actual number was less than 700 operational aircraft. The Luftwaffe had more than 3,000 fighters and bombers ready for action. Britain wasn't winning because their pilots were better trained. German pilots had combat experience from Spain and Poland. Many British pilots had never fired their guns in anger before July 1940. Britain was surviving because of a secret weapon that existed in exactly 21 locations along the British coast. A weapon so new that most people, even in the military, didn't understand how it worked. This weapon could see the invisible. It could detect aircraft 80 miles away, long before any human eye could spot them. It could count them, measure their altitude, track their speed, and predict where they would cross the coastline. The British called these installations chain home stations. Each station consisted of enormous steel towers, some reaching 350 feet into the air, higher than the Statue of Liberty. From these towers, invisible waves of radio energy pulsed out across the channel, washing over everything in their path. When these waves struck something metal, like an aircraft, they bounced back. Receivers captured these returning echoes and translated them into information: range, bearing, height, number of aircraft. But in August 1940, radar was so new, so experimental, that the men who operated it were making up procedures as they went along. The equipment broke down constantly. Vacuum tubes burned out. Transmitters overheated. Receivers drifted off frequency. Lightning strikes could fry entire systems. Every station kept spare parts, but there were never enough. Engineers worked miracles daily just to keep the systems running. The station that matters to our story stood on the cliffs near Ventnor on the Isle of Wight. Ventnor was critical. Its position gave it coverage of the central English Channel, the most direct approach to London, and the naval base at Portsmouth. When Ventnor was operational, the RAF had roughly 15 minutes warning before German formations reached the coast. 15 minutes to scramble fighters, gain altitude, and position themselves for intercept. Without Ventnor, the Germans could be overhead before British fighters could even take off. On August 15th, the Luftwaffe had tried something different. Instead of targeting airfields and aircraft factories, they attacked the radar stations themselves. Ventnor took a direct hit. High explosive ordnance destroyed the operations building, damaged the towers, and threw debris across the compound. 3 people lost their lives. The station went offline. Engineers worked around the clock. They jury-rigged temporary repairs, bypassed damaged circuits, and substituted equipment cannibalized from other systems. By the morning of August 18th, they had the station barely functioning. The radar could detect formations, but the picture was fuzzy, unreliable. Range estimates were questionable. Height readings were erratic, but it was working, barely. And then, at 1437 hours, as the largest German raid of the day approached the channel, the main transmitter failed completely. The fault occurred in the modulator stage, a complex assembly of transformers, capacitors, and vacuum tubes that shaped the radar pulse. Without the modulator, the transmitter couldn't generate the precise burst of radio energy needed for detection. The system was as useless as a flashlight without batteries. The senior operator immediately called for the engineer on duty. His name was Sergeant Leonard Thomas. He was 24 years old. Before the war, he had repaired radios in a shop in Cardiff. He had joined the RAF in early 1939, trained as a radio mechanic, and found himself assigned to this new mysterious thing called radar, or RDF, as they officially called it, radio direction finding, because the word radar hadn't been invented yet. Thomas sprinted to the transmitter building. He could hear the cooling fans winding down. The smell of ozone and hot electronics filled the air. He pulled the access panels and immediately saw the problem. The main modulator transformer had failed. Not just failed, but failed catastrophically. The transformer was a custom-built unit, impossible to replace. There were no spares. The nearest replacement was at a depot 50 miles away. Even if they sent a motorcycle courier immediately, it would take 3 hours minimum. The operations room was on the telephone. German formations were building over Calais. Intelligence estimated at least 400 aircraft. They would reach the British coast in under 20 minutes. Fighter Command needed Ventnor operational. Squadrons were already scrambling based on reports from other stations, but Ventnor's coverage was crucial for precise intercept vectors. Thomas stood in that transmitter room, staring at the ruined transformer, and his mind raced through the problem. A transformer is essentially simple technology, coils of wire wrapped around an iron core. But the modulator transformer was special. It had to handle enormous voltages, tens of thousands of volts, for microsecond pulses. The windings had to be precise. The insulation had to be perfect. One tiny fault and the whole thing would arc over and destroy itself, which is exactly what had happened. He couldn't replace it. He couldn't repair it. The copper windings were fused together, the insulation was charred, and the core was likely contaminated with vaporized metal. But maybe, just maybe, he could bypass it. Thomas ran outside to the equipment yard. Every radar station accumulated a collection of damaged and obsolete equipment that was too expensive to throw away, but too broken to use. Spare parts for systems that no longer existed. Failed components waiting for depot-level repair. Experimental gear that hadn't worked out. The engineers called it the Scrapyard. He tore through it, pulling aside crates and boxes. He needed a transformer. Any transformer. It didn't have to be perfect. It just had to work well enough to get the system back online. He found what he was looking for in the third crate he opened. An old transformer from a different model of transmitter, pulled from a prototype system that had never gone into production. The voltage rating was wrong. The power handling was marginal. The mounting brackets wouldn't fit. But electrically, theoretically, it might work. Thomas grabbed it and ran back to the transmitter building. He had no time for careful work. He ripped out the destroyed transformer with bolt cutters, not even bothering to disconnect it properly. He positioned the replacement transformer and realized immediately that it was too small for the original mounting points. So he didn't mount it. He set it on the floor, propped against a rack, and started connecting wires. The replacement transformer had different terminals. Thomas didn't have the right connectors, so he stripped wire ends with his pocket knife and twisted them together. He didn't have tape, so he wrapped the connections with paper towel torn from the supply closet and hoped it would insulate well enough. The voltage ratings were wrong, so he had to add a series resistor to drop the voltage. He didn't have the right resistor value, so he connected 3 smaller resistors in series, holding them together with twisted wire. 2 minutes had passed. He needed to connect the output, but the transformer's secondary winding had the wrong phasing. If he connected it directly, the timing of the radar pulse would be inverted. The system wouldn't work. He had to reverse the connections, but there wasn't space to physically swap the wires. So he added a jumper, routing one wire across the front of the panel while the other went behind. It was ugly. It was dangerous. Any electrical engineer would have been horrified. But it should work. 3 minutes had passed. Thomas closed the access panel, not even bothering to install all the fasteners. He ran to the control position and signaled the operator. The operator looked at him with a mixture of hope and doubt. 3 minutes to fix a catastrophic failure. It wasn't possible. But Thomas nodded. The operator threw the master switch. The cooling fan spun up. The high-voltage indicator lights began to glow. The pulse monitor showed green. The operator watched his displays, hardly daring to breathe. And then, blooming across the plotting scope like a constellation of green stars, the returns appeared. Multiple contacts bearing 120 degrees, range 73 miles, altitude showing between 15 and 20,000 feet. The picture wasn't perfect. The returns were fuzzy, the altitude reading was approximate, and the range estimates were probably off by a few miles. But it worked. The radar was operational. The operator grabbed the telephone. Ventnor to filter room. Radar operational. Multiple plots, large formation, approaching sector. The information flowed through the defense network. Filter room to group operations to sector control to the squadrons already climbing for altitude over Sussex and Kent. Squadron leader James Nicholson was leading Red Section of 249 Squadron when the updated vector came through. Turn to heading 200. Climb to Angels 20. The information was precise now, not a guess, not an estimate based on Observer Corps reports from the coast. Precise coordinates generated by Sergeant Thomas's scrapyard repair job. Nicholson's section intercepted the German formation 30 miles from the coast. 12 Hurricanes against more than 100 bombers and their escorts. Terrible odds. But the Hurricanes had position. They were above the bombers, diving out of the sun, exactly where they needed to be. The German formation scattered. Bombers jettisoned their loads early, trying to gain speed to escape. The Messerschmitt escorts had to break formation to engage the Hurricanes. Other squadrons arrived, vectored in by the same radar information. More Hurricanes, Spitfires from 152 Squadron, even a few Defiants from the night fighter units. The air battle spread across 100 square miles of sky. Aircraft twisted and dove, trailing smoke and fire. The thunder of engines and guns rolled across the countryside below. When German bombers did reach their targets, they were scattered, disorganized, and under constant attack. Their bombing was inaccurate. Many formations turned back before reaching their objectives. The raid that German planners had intended as a knockout blow became a confused, costly engagement that achieved almost nothing of strategic value. Meanwhile, on the ground at Ventnor, Sergeant Thomas watched his improvised repair with the attention of a man expecting disaster at any moment. The replacement transformer was running hot, very hot. The paper towel insulation was turning brown. The twisted wire connections were starting to oxidize. The whole assembly vibrated with each pulse, threatening to shake itself apart, but it held, pulse after pulse, hour after hour. It held. The air battle lasted 3 hours. Ventnor's radar operated continuously, providing the tracking data that allowed Fighter Command to vector reinforcements, redirect squadrons as the tactical situation changed, and maintain constant pressure on the German formations. When the last German aircraft turned for home, pursued by British fighters all the way to the French coast, Ventnor was still transmitting. Only after the all-clear sounded did Thomas finally shut down the radar. He opened the access panel and found the transformer so hot he couldn't touch it. The paper towel insulation had partially charred. One of the twisted connections had actually started to melt. But it had worked. The official records show that on August 18, 1940, the Luftwaffe launched multiple large raids against Britain, losing 69 aircraft to all causes. British losses were 27 aircraft, but most of the pilots were recovered. The raids failed to achieve their objectives. The invasion of Britain, already problematic, became increasingly unlikely, but the records don't show what might have happened without Ventnor's radar. They don't show the bombers that would have reached their targets unopposed. They don't show the factories that might have been destroyed, the aircraft that might never have been built, the pilots who might have been caught on the ground. The mathematics of aerial combat are brutal. A squadron caught taking off is destroyed. A squadron with altitude advantage survives. The difference between success and catastrophe is measured in minutes and thousands of feet of altitude. Sergeant Thomas's 3-minute repair job bought those minutes. It bought altitude. It bought time for fighters to position themselves correctly. It bought information that turned a defensive scramble into an aggressive interception. Let me give you some context about just how critical radar was becoming. In the early months of the Battle of Britain, from July through early August, the RAF was losing pilots faster than training schools could replace them. Not necessarily because German pilots were better, but because the Germans had initiative. They chose when and where to attack. British fighters were scrambling reactively, often arriving too late or in the wrong position. Radar changed that equation. With radar, Britain wasn't reacting to attacks. Britain was anticipating them. Fighters could be climbing for altitude while German formations were still over France. Controllers could vector squadrons to intercept positions based on calculated tracks, not guesswork. A Hurricane squadron positioned correctly could engage a German bomber formation, inflict heavy damage, and be diving away before the escort fighters could intervene. The Germans knew about radar. German intelligence had photographed the chain-home towers. They knew the stations were important. That's why they bombed Ventnor on August 15th. But German intelligence fundamentally misunderstood how the system worked. They thought radar was a detection system, useful but not crucial. They didn't understand it was the nervous system of the entire British defense network. They didn't understand that every radar station was linked to a filter room, which was linked to group operations, which was linked to sector control, which was linked directly to the fighters in the air. When a radar station went offline, it wasn't just a gap in coverage, it was a break in the command and control network. Controllers lost situational awareness. Response times increased. Fighters arrived late or in wrong positions. The entire defense became less efficient. This is why Thomas's repair mattered so much. Ventnor wasn't just another radar station. Its position on the Isle of Wight gave it coverage of the most direct route to critical targets: Portsmouth Naval Base, Southampton Docks, the Spitfire factory at Supermarine, the Hurricane factory at Hawker. When Ventnor was operational, attacks on these targets required German formations to run a gauntlet of intercepting fighters vectored precisely to intercept positions. Now, I need to tell you something important about Thomas himself. He wasn't a genius engineer with advanced degrees. He was a radio mechanic who had learned his trade fixing civilian radios in a shop. But he had something more valuable than formal education. He understood how things actually worked, not just in theory, but in practice. He knew that perfection was the enemy of operational. He knew that a working solution, even an ugly one, was better than an elegant solution that took too long. This mindset was crucial in 1940. British engineers were dealing with cutting-edge technology that barely worked under ideal conditions. Radar sets were temperamental. They needed constant adjustment. Components failed regularly. The engineering manuals were sometimes wrong because the technology was so new that nobody really understood all the failure modes yet. The engineers who succeeded were the ones who could improvise, who could look at a broken system and figure out a workaround using whatever materials were available. Thomas's scrapyard repair was typical of the kind of inventive, seat-of-the-pants engineering that kept Britain's radar network operational. After the war, historians analyzing the Battle of Britain identified several critical factors in the British victory. Superior fighter aircraft, particularly the Spitfire, brave and skilled pilots, fighting over home territory, allowing downed pilots to return to duty, good leadership at fighter command, particularly Air Chief Marshal Hugh Dowding. But increasingly, historians have recognized that the most important factor was the integrated defense system, and the heart of that system was radar. Without radar, Britain would have had to maintain constant standing patrols, which would have exhausted pilots and worn out aircraft. Without radar, controllers would have been guessing about raid composition and direction. Without radar, the numerical advantage Germany enjoyed would have been decisive. Thomas's contribution to this system was 3 minutes of improvised engineering under pressure. But those 3 minutes in that transmitter room had consequences that rippled through the entire battle. The German formations that scattered on August 18th went back to France and reported heavy fighter opposition. Luftwaffe intelligence revised their estimates of RAF strength upward. German planners had to reconsider their timeline for invasion. The psychological impact on German bomber crews was significant. If they couldn't penetrate British defenses, even in raids of 400 aircraft, how could they possibly neutralize the RAF? The improvised repair lasted 3 days. On August 21st, a proper replacement transformer arrived from depot. Engineers installed it correctly with proper mounting, proper connections, proper insulation. The scrapyard transformer, when they removed it, was barely recognizable. The case was discolored from heat. The terminals were corroded. The insulation was charred. Any electrical inspector would have condemned it as dangerous, but it had worked when it needed to work. Thomas received a commendation from his commanding officer. The written citation mentioned resourcefulness and technical skill under combat conditions, which seems inadequate for 3 minutes that helped change the course of a battle. But that was typical of such citations. The nature of technical support means that successes are quiet and invisible, while failures are spectacular and obvious. Let me put this in broader perspective. Wars are won and lost on logistics and maintenance, as much as tactics and bravery. For every pilot flying a Spitfire, there were dozens of people keeping that Spitfire airworthy: mechanics, armorers, fuel handlers, clerks, drivers. For every radar operator tracking German formations, there were engineers like Thomas keeping the equipment running. These support roles don't get the same recognition as combat roles. There are no exciting stories about a mechanic changing spark plugs. Nobody makes films about engineers soldering connections. But without these unglamorous jobs being done well, the exciting combat operations become impossible. Thomas's story illustrates a truth about technology in warfare. The most sophisticated equipment in the world is useless if it doesn't work. Reliability matters more than capability. A simple system that works is better than a complex system that's broken, and the ability to maintain and repair equipment in field conditions under pressure with limited resources is as important as the original design. British radar in 1940 wasn't the most advanced radar technology. German engineers had developed radar too. American research was in some ways more sophisticated, but British radar worked reliably, was properly integrated into command and control systems, and was maintained by engineers who could keep it operational under combat conditions. The German attack on radar stations was actually a brilliant tactical idea. If they had persisted with it, if they had systematically destroyed the chain-home network, the Battle of Britain might have turned out very differently. But after the August 15th attacks, German planners shifted focus to other targets, partly because they underestimated radar's importance. Partly because the stations were hard to destroy completely. They could be damaged, but were quickly repaired. This decision to shift away from targeting radar was one of the critical German mistakes of the battle. They failed to press an attack that was actually working. Instead, they went after airfields, factories, and eventually cities, none of which proved decisive. Meanwhile, engineers like Thomas kept the radar network operational. They improvised repairs. They scavenged parts. They worked around limitations. They found solutions that wouldn't be in any manual because the manuals didn't exist yet. This unglamorous, invisible work was as important to victory as anything happening in the air. I want to be clear about the scope of what happened on August 18th. This wasn't a single decisive battle. It was one day in a campaign that lasted months. But it was a day when the Luftwaffe committed major resources to an attack that largely failed. And it failed partly because British controllers had good situational awareness, which allowed them to vector fighters efficiently. And they had good situational awareness partly because Ventnor radar was operational. And Ventnor was operational because Sergeant Thomas spent 3 minutes improvising a repair with scrapyard parts. Cause and effect in warfare is complicated. You can't draw a straight line from one event to one outcome. August 18th wasn't the turning point of the Battle of Britain. There were multiple turning points, multiple critical moments. The failure of German strategy in early September, when they shifted to bombing London instead of maintaining pressure on airfields. The success of British aircraft production, which kept pace with losses despite German attacks on factories. The exhaustion of German bomber crews flying mission after mission without achieving decisive results. But August 18th was a day when things could have gone differently. If Ventnor had remained offline, if German formations had reached their targets with less opposition, if British losses had been heavier and German losses lighter, it might have reinforced German confidence and demoralized British defenders. The psychological dimension of the battle mattered as much as the physical one, and on that day, at that moment, in that transmitter building, Thomas made a decision. He could have told his officers that the repair would take hours, that they needed the proper parts, that he couldn't guarantee a field expedient would work, all of which would have been completely reasonable and entirely defensible. Instead, he took a chance. He grabbed whatever he could find, threw together a solution that violated every proper engineering practice, and hoped it would hold. That kind of decision-making, that willingness to take risk and improvise, was characteristic of the people who won the Battle of Britain, pilots who pushed damaged aircraft beyond their limits to get back to base, controllers who made split-second decisions about where to commit their limited fighters, ground crews who turned around aircraft in minutes instead of hours, and engineers who fixed broken equipment with whatever came to hand. Thomas served through the rest of the war. He was eventually promoted to sergeant major and ended up at a radar training school, teaching new engineers the technical skills and, more importantly, the improvisation mindset that kept equipment running. After the war, he went back to Wales and opened his own radio and television repair shop. He rarely talked about his wartime service. In photographs from the period, he looks like 1,000 other young men in RAF uniform, serious, unremarkable. But for 3 minutes on August 18, 1940, he was the most important person in the British defensive network. In those 3 minutes, working with scrap parts and twisted wire, he kept a critical system operational at a critical moment. The Battle of Britain was won by many people making many decisions over many months. Dowding's careful management of fighter resources, Park's tactical flexibility at 11 Group, the bravery of pilots who flew and fought when they were exhausted beyond imagining, the workers in factories who built Spitfires and Hurricanes faster than they could be destroyed, the civilians who endured bombing and kept essential services running. And somewhere in that vast collective effort, Sergeant Leonard Thomas spent 3 minutes with a scrapyard transformer, and the radar stayed operational, and fighters were vectored correctly, and the battle that day went Britain's way. This is the nature of warfare. Grand strategy matters, leadership matters, technology matters. But at critical moments, outcomes can turn on small things. A supply convoy that gets through when it might have been sunk. A bridge that holds when it might have collapsed. A radio message that gets through when it might have been garbled. A radar that works when it might have failed. Thomas's story reminds us that history isn't just made by famous people making famous decisions. It's made by thousands of people doing their jobs well at moments when it matters. The mechanic who does a thorough pre-flight check and catches a fault that would have caused an engine failure. The clerk who files a report properly so intelligence analysts can spot a pattern. The radio operator who stays at their post and relays a crucial message. These moments don't make the history books. There's no memorial to the unknown engineer. But these moments shape history as surely as the famous battles and famous decisions. On September 15th, now commemorated as Battle of Britain Day, the Luftwaffe launched its largest daylight raid against London. It was meant to be the knockout blow, the attack that would break British resistance and force Churchill to negotiate. Instead, it became a catastrophic German defeat. The RAF shot down significant numbers of German aircraft, while British losses were comparatively light. Why did September 15th turn into such a decisive British victory? Many factors. But one factor was that the radar network was fully operational, providing complete coverage of German formations from the moment they left French airfields. Controllers had perfect situational awareness. Fighters were vectored to exact intercept positions. The British defense worked exactly as designed, and that network was operational partly because engineers throughout August had kept it running despite attacks, despite equipment failures, despite every problem that arose. They maintained a technological edge that gave Britain a fighting chance. Thomas's 3-minute repair in August was one small contribution to that larger effort. But in warfare, small contributions add up. A battle is won by 1,000 small things done right. And sometimes, when you're lucky, the small things get done right at exactly the moment they matter most. The transmitter room at Ventnor still exists, now part of a museum. You can see the original equipment, carefully preserved. The transformer that Thomas installed as a permanent replacement is there, properly mounted, properly connected, everything by the book. But the Scrapyard transformer, the twisted wire connections, the paper towel insulation, those are long gone, thrown away after the proper repair was completed. Which seems appropriate somehow. The improvised repair was never meant to last. It was meant to work right now, in this moment, when it was needed, and it did. That's all that mattered. War is often described in terms of great battles, brilliant strategies, heroic actions, and those things are real and important. But war is also about maintenance schedules and spare parts inventories and repair procedures. It's about keeping equipment running when it doesn't want to run. It's about finding solutions when there are no good options. It's about a 24-year-old sergeant from Cardiff standing in a transmitter room with a destroyed transformer, with German bombers approaching, with no spare parts and no time, and deciding that maybe, just maybe, there's something in the scrapyard that might work. 3 minutes. That's all it took. 3 minutes to save a radar station, which helped win an air battle, which contributed to winning a campaign, which helped change the course of the war. History turns on such moments. Small decisions made under pressure by people whose names are mostly forgotten, but the consequences of those decisions echo forward, shaping everything that follows. Sergeant Leonard Thomas made one such decision on August 18, 1940. He didn't have time to think about consequences or historical importance. He just had a job to do, and he did it with whatever he had available. And because he did his job well, in that moment when it mattered, the radar stayed operational, and that made all the difference.